Hello and welcome to Wednesday's edition of Cracking the Cryptic, where yesterday we did the most lovely but quite easy puzzle by the great Marty Sears. And I mentioned in that video that the testers have been having the devil's own job trying to solve another Marty Sears puzzle that had been recommended to the channel called Yin-Yang-Yong. Anyway, we then get a lot of emails overnight saying, oh, please can you solve Yin-Yang-Yong by Marty? So, in a very rare thing on Cracking the Cryptic, we are going to do back-to-back Marty Sears, well, hopefully back-to-back Marty Sears puzzles, because I've got to solve this myself, and I know this is hard, because two of the testers couldn't do it. But I did find it on Logic Masters, and I snipped some comments. So it clearly is possible. People have solved it. But it is described, look at this, brain-bustingly hard, says Chinstrap, who's very clever. So that is slightly terrifying. Blackjack fits, classic Marty Sears, brain-bending but in the best possible way. Rat thinks, another stunning Marty deduction that broke my brain. A Prof. Dory, that must be, is that Dorlia? It might be. Yin-Yang-Yong Yonk, says Heliopolis, a beautifully weird puzzle. Magnus Josephson, one of the Josephson twins, sort of genius level intellect, fantastic and so much fun. So, yeah, this is not, though, it's not even a chaos construction. So it may look like a Sudoku, but it's called a Sumdoku. And this is a weird rule set. I've only done 2 or 3 of these puzzles, I think, in my life. And the idea is that, so for example, in row 4, there are 4 different digits in row 4. In row 6, there are 6 different digits. So it's weird. It's a weird rule set. Anyway, we'll do battle with this. It's got 5 stars out of 5 for difficulty in a moment or two's time. We'll read the rules together then. What can I tell you about? Well, I have a bit of an apology to make, because I'd hoped that this morning at 10 a.m. we would release the continuation video from Monday night's stream. So Mark and I streamed Blueprints again on Monday night. At about 10 past midnight, we gave up on a day because it was so late. And I then finished that day the following morning, and I recorded it. And the recordings worked. Everything's fine. But when I came to upload that to YouTube today, my internet has gone to sort of antediluvian speeds. I'm not actually sure whether it's my internet or whether YouTube's upload speed has gone to pot today, but it's 2.5 hours was the upload time, and it's not that long a video. So hopefully, internet allowing, that will go live tomorrow at 10 a.m. UK time. So if you have been waiting for that, I'm sorry. I did try, but I was foiled by technology, as so often happens. What else can I tell you about? I've got some birthdays to do. Well, okay, let's talk about our monthly competition, which is running. Started on the 1st of December. Over on Patreon, the Wind in the Willows. The feedback so far, actually I've got to refresh the count. We were at 716 solves and 38. So where are we now? We are at nearly 1,000 solves of the first puzzle and 97 solves of all of them. That's phenomenal. Yeah, the feedback is that there are quite a few approachable puzzles in the pack. So if you are new to sort of variant Sudoku, or if you're new to our Patreon rewards, you'll get through some of these. And the feedback's been great, actually. So I think we've got the difficulty level about right this month. And you can see there are 13 puzzles in all. Help Mole to sort of find and open advent calendar. And I think if you're familiar with the book, you might recognise some of those puzzle titles there. So that's over on Patreon right now. Right, let's do the birthdays. Ellie, you've turned 22 today. Apparently you've been watching for nearly 2 years. And you used to only watch the videos, but now you solve all the puzzles as well. 2 puzzles a day. That is phenomenal. I love hearing how people go on a puzzle journey. So they may sort of you know, lightly get into the videos. They're sort of intrigued by the logic, but assume wrongly they'd never be able to solve them themselves. And then they do start to solve them themselves. I mean, actually, yesterday's Marty Sears puzzle is a great way to convince yourself you could solve them. And then like Ellie, you become an expert. So Ellie, many happy returns today. I hope you have a brilliant birthday, and I hope the chocolate cake is very well iced. Now, another 22 birthday, Plum. Plum, you've turned 22. I think you might be in New Mexico. I hope I've remembered that correctly. But you're planning a night at the bar to celebrate your birthday, and a cake. You're not sure where the cake is going to be sourced from. So, Plum, I hope you enjoy your night at the bar, and I hope you have a great birthday, and that cake is up to snuff when you find it. Next, Ashley. Ashley, you've turned 39 today, and I know this because your husband Anthony, from over there in North Dakota, Michigan, wrote to me. And the two of you, you love icy fruit puzzles. I sort of love icy fruit puzzles as well. And you love Marty Sears puzzles. Well, this is halcyon days, yesterday and today. And you enjoy the blueprint stream. So yeah, and tomorrow as well then. And Ashley, you love cake, but Anthony doesn't. Well, that's good. It's your birthday, so you can have what you like. And I hope the cake is very good and very well iced. And then finally, Christina. Your partner Vlad wrote to me and said that you follow all the puzzles, and Vlad thinks you'll be pleasantly surprised if you hear your name in the video. I hope that's true. It'd be awful if it was a bad surprise, wouldn't it? I haven't heard from anyone for whom it was a bad surprise. But Christina, I hope it's a nice surprise, and I hope you have a brilliant birthday today, and you find some heavily iced chocolate cake. Now, we can resist it no longer. I'm nervous about this one. Let's have a look at the rules. Yin-Yang-Yong by Marty Sears. The rules are as follows. We have got a sum doku, which means we have to fill each cell with a digit from 1 to 9. For every row n and column n, there are exactly n unique digits. The remaining cells are filled with repeats. So in row 5, there will be 5 unique digits. So say 1, 2, 3, 4, 5. They don't have to be the numbers 1, 2, 3, 4, and 5. They can be anything. And then these would have to be made up of the digits 1, 2, 3, 4, and 5 in some order. So there were 5 unique digits and some repeats. Right, it doesn't get any easier, believe me. Yin-Yang-Yong. Divide the grid into 3 regions. A region is an area of orthogonally connected cells. No 2x2 area may be entirely in one region. So this is like, well, yin-yang would say divide the grid into 2 regions. And sometimes for that one, I sort of do this colouring to indicate yin-yang logic. So let's start from that and see if we can extend it. So, yes, you can see in this pattern all of the purples are orthogonally connected. Orthogonally connected means share an edge with other purples. So we couldn't make that one purple, for example, because this purple sits on its own. Doesn't share an edge with other purple cells. And there, but in this puzzle, we've got to do another colour as well. So maybe if I do that, I mean, I know that's a very simple adjustment, but is that correct now? Probably is. It feels like it should be. Yeah, so maybe I can make that more complicated and sort of do this. Yeah, I mean, I think this sort of thing is what we have to do. All the blues are connected, all the greens are connected, all the purples are connected, and there's no 2x2 of any one colour. So that's a possible yin-yang-yong shading. Now there are more rules. We have got, oh good grief, right. Identical digits may not appear in different regions. Right, so that, Yeah, so the Yin-Yang-Yong shading, the three region division. So let's go back. Let's go back to my three region division. So I think what that's saying is if that's a 1, that couldn't be a 1, I think. Because these are identical digits and they are in different regions. So I don't think you're allowed to do that. That's my reading anyway. Right, we've also got German Whisper, green. Okay, that must be these. Adjacent digits on a green line have a difference of at least 5, so that's normal rules. So if that's a 1, that's either 6, 7, 8 or 9 to be sufficiently different from the digit 1. Nabna, yellow. So no two digits anywhere on a yellow line may be consecutive or the same. Right, so if that's a 5, this digit cannot be 5, 4 or 6 because any of those would breach that rule. Entropic, orange. Gosh, I'm going to think these are Dutch whispers, aren't I? So entropic, any group of 3 adjacent cells on an orange line must contain one low digit, one medium digit and one high digit. And a low digit is a 1, 2 or a 3, a medium digit is a 4, 5 or a 6, and a high digit is a 7, 8 or a 9. God, actually there's quite a few more rules. Same difference, turquoise, that's this one. Adjacent digits on a turquoise line must always have the same difference. This difference must be determined for each turquoise line. Right, so let's say that the difference on this line was 3. This line could go 1, 4, 7. I mean, actually, I've just thought of something horrendous as well. Because this is a Sudoku, it could go 1, 4, 1. Normally it couldn't because Sudoku would be broken. But there is only... I think the only place you can do Sudoku in a Sudoku is in row 9 and column 9. I might be wrong about that, but that's sort of how I think about them. Alright, so that's a rule. X, digits joined by an X sum to 10. So those sum to 10, those sum to 10, those sum to 10. Blue arrow. Okay, that must be these. A digit on a blue arrow indicates how many region borders separating 2 regions are seen in the direction of the arrow. Region edges at the outer perimeter of the grid don't count. Yeah, okay, so actually let's draw in a border around the edge. I always like doing this. So I think what that's saying is, let's make that a colour, and let's say that this is the same colour but this is a different colour. And then this is let's use blue, and then it goes back to purple, and then it goes back to blue again. So if this was the arrangement of colours or regions, this clue is counting region borders. So there's a border there between pinkle and indigo. 1, 2, 3. I think that would be a 4. I think 1, 2, 3, 4. And this one, the one at the very edge of the grid where my cursor's moving, that doesn't count, is what the rule is saying. So it's all quite straightforward. No problem at all. Do have a go. The way to play is to click the link under the video as usual. But now I get to play. Let's get cracking. Now, I alluded in the instructions to the fact that I know hardly anything about Sudoku, but the thing I do know is because row 1 and column 1 are allowed to have one digit in them, one unique digit. These are all the same digit. So we should just... The thing is, that might not be a 1. So what should we call that digit? Let's call it a letter. Let's call it A. Yeah, and I also said that row 9 and column 9, they are the... So row 1 and column 1 we sort of know something absolutely definitive about. row 9 and column 9 we also know something definitive about, in the sense they have to have 9 unique digits in them. So they have all 9 Sudoku numbers. So I can't do what I was going. Oh, I can sort of do it. I'm going to do this. That's true, but obviously I can't mimic that down here because I don't know whether this might be B, but it doesn't have to be B. You know, that could be, it just has to be different from A and I in the column. Now, I don't know why I'm doing this anyway. I know there's going to be some trick to do with Yin-Yang-Yong that I've got to sort of unearth here. Oh, right, okay. Oh, this is horrendous. Right. So in column 2, using my nomenclature, which is saying that this is digit B, because in column 2 I'm only allowed 2 different digits, all of those cells are either the digit A or the digit B. I'm just thinking that it'd be classic Marty if A is 5, wouldn't it? Because normally, of course, you can't put double 5 on an X across an X, but you absolutely can in some doku, because there's going to be repeats. Oh, bobbins, I don't know what to do then. So, okay. So in column 3, we've had the digit C and the digit A. Now this entropic line has to have one of each entropy. Now that means A and C, because this line will have A and C on it, and it'll have some other digit. Yeah, so if that digit is B, then this row would be AB as well, wouldn't it? Because in row 2 I've got only got 2 digits. So if that's B, that specifies that this row is AB. Oh no, that could still be A. I was thinking maybe this has to be ABC, but I don't think that's true actually, because that could be A and then one of these is C, and then you could have another letter on the entropic line. Oh, right, so the digits that are in row 2, A is one of them. So A is definitely on there, because these can't be the same digit. They're on a German whispers line. Okay. All right, that's quite funny. That's quite funny, because my concern was that this arrow, or this X, was double 5. That's actually not true. A can't be 5, because in row 2, A is one of the digits. There's only 2 digits in row 2. We don't know what the digits are, but we know one of them is definitely A. So A is on a green line. And what do we know about green lines and the digit A? Well, no. No, what do we know about green lines? We know they can't have the digit 5 on them. Because if they have 5 on them, what digit will be partner the 5 with? Nothing qualifies. If you go, because you need a digit that's 5 different. If you go downwards, you get to 0 or negative numbers. If you go upwards, you get to 10 or higher. So that doesn't work. So actually, right, hang on. So this is B then, I think. Because once these 2 digits are not the same, they have to be different. So that actually is B. So A and B sum to 10. but we don't know that A and B are on this. You see, if that's B, then you do know that. Oh, hang on. This is yin-yang, isn't it? This is important. Ah, yeah. Okay, so let's just spend a few moments, because I've spotted something. I think this does have to be B, and that's going to be useful. Let's take a couple of moments to think about how yin-yang, or at least yin-yang works, and then we'll try and introduce yang as well. But what we're told at the start of the puzzle is that these digits here, I mean, they are the digit A, and they've all got to be in the same region. So I can colour those the same. They all have to be the same digit, I think. Well, they're all the same digit, that's true, but they all have to be in the same region, because if some of them were in a different region, you'd have the same digit in different regions, which is expressly against the rules. But what I'm thinking is, now this cell, by yin-yang logic, can't also be a green digit. So if this was A, it would be green, and that would be a 2 by 2. So that is the digit B. And that's the digit B. So those two are a different colour. And okay, and that's the same. So B is in those three positions. Right, hang on. Because now, what's that digit? That's B. Because in this row I only put A and B in now. Now I know that B is in row 2. This whole row is only full of A's and B's. And this digit in column 9 is not allowed to be A, because there are 9 different digits in column 9. And now, now I'm wondering if I'm allowed to join these up. This is very okay. I'm not good enough at yin-yang. Well, no, I'm okay at yin-yang, I think. I'm not good enough at Yin-Yang-Yong. So in yin-yang, if there were only 2 regions in this puzzle, then one thing I know is that you couldn't say make this cell green. In fact, you can't make it green in this world. And the reason for that is to do with sort of checkerboard logic. So let's just look at a very simple checkerboard. So let's examine a 2 by 2. Now, if you had 2 purples and 2 greens in a 2 by 2, could that work in this sort of Battenberg arrangement? And the answer is no, because there's a requirement we join together the purples using an orthogonal connection. And however we did that, it wouldn't be possible to then orthogonally connect this green to this green, so the rules would be broken. Now, if we then extend that logic and look at a whole perimeter of a yin-yang puzzle, not yin-yang-yong, just yin-yang, then we can have 2 stretches of colour in the perimeter, but we can't introduce a third. So we can't revert to green here, because to connect this green to the rest of its green friends, however we did that, we would form a wall that would prevent us orthogonally connecting this purple to this purple. So what happens in yin-yang at least, is that you'd have to connect all of these up. But that's definitely not necessarily the case here, I've realised that. Because what you could have, imagine that cell was the 3rd colour, let's make it orange. Then it could be in a region over here. That's absolutely fine. And then these could join up somehow. That would be fine. And we'd have to do this to avoid 2x2s, etc. But providing orange never touched green, it would always be possible to connect these two B's together. So, okay, so in a Yin-Yang-Yong, you don't have to... I don't think it's necessary that I connect these I don't think it's necessarily the case I do that. I mean, if I did do that... Well, if I did do that, the puzzle, I couldn't obey... Well, no, actually, that's interesting. I couldn't obey the rules of the puzzle, actually. The reason that wouldn't be possible is I've made all of the digits either A or purple. They're either green or purple, because in row 9, I've got all the different digits that are going to appear in this puzzle. They are present in row 9. So I've got A, whatever A is, and then I've got B, C, D, E, F, G, H, and I that are all in the purple set. So there are no orange digits at all. So the whole grid would be green and purple. Now it says in the instructions, divide the grid into 3 regions. I couldn't do that. I could only divide it into 2. Okay, now that's a slightly specific way of saying that this isn't correct, but I can see another way. Let's imagine for a moment that I couldn't use the words of the rules to say this arrangement is invalid. I can still prove this arrangement isn't valid, because how am I going to fill row 8? If this was right and the whole perimeter was just coloured like this, how would we fill row 8? And the thing I'm specifically thinking about is avoiding 2x2s in purple. Because in row 8, I'm meant to have 8 different digits. And we can see from this arrangement, I'd have to make this green to avoid a 2x2 here. But now, I can't have any more repeats, so I can't have any more A's in this row. And that means all of these are purple. And there is a whole multitude of 2x2s down here, which isn't right. So I think whether we just use the rules to say, well, I haven't divided the grid into 3 different colours, or whether I use that extended logic to do it, it is not possible that these B's connect around the perimeter. And that's really interesting, because what that means, no jokes, I do find that interesting, genuinely do. It's like I found it interesting today. I was looking at TikTok, and apparently, if you divide any prime number by 4, and there is a 1 remainder, then that prime number can be expressed as the sum of 2 primes. And Fermat proved that, apparently. And that was very interesting. I found that interesting as well. See? Anyway, you all knew that anyway. I didn't know that. Now I've got distracted. Yeah, so what I was going to say is now, because I definitely can't put A on this perimeter, because that's going to cause the exploded checkerboard problem. So there is some new colour. So doesn't that mean this always has to be orange? I think it does. That might be wrong. Imagine F was orange. And so what I'm saying is it possible I is not orange? I don't think it is, because if F was orange, F is appearing in this column somewhere, doesn't matter where, let's make it there. And this is not orange, so this is either, well, this can't be green, so it would have to be purple, and now we've got an exploded checkerboard problem again, because to join that B to that I, however I do it, I'm isolating this F from this F. So that is logical. That is definitely orange. This cell in the corner is orange. And I presume, although I'm not stating this for fact, but I presume it's going to have to grow a bit. And actually, it's going to have, that's really weird. It's going to have to grow by the same amount on both sides, I think. Otherwise, we're going to run into exploded checkerboard problems again. Because imagine that. Well, if H is not orange, we know it can't be green, because that's going to lead to exploded checkerboard, so it would be purple. And now if H wasn't here, and was anywhere else, that would imply one of these was orange, and I'd have to loop round to connect the oranges, and the H's couldn't connect. So, and I think that logic just propagates. So if either both of those are, which is going to make all of that. Oh, hang on, this doesn't, I'm sure this doesn't work. So I'm now wondering whether or not, but the thing with Marty is you've got to be careful with Marty, because Marty would just find it funny. He would find it funny to say divide the grid into 3 regions and there'd be only one colour, one cell of the 81 cells, to have only one cell. That would be quintessential Marty Sears. So I am not falling for that. I'm not assuming that this is not the only orange cell in the grid. But no, that can't be right. Sorry, I'm being dumb. I'm being dumb. Because if this was the only, I exists 9 times. No, that's not true. It doesn't, does it? Oh gosh, no. Forget Sumdoku, Simon. It's Sumdoku. So yeah, that could, no, okay, so I'm going back to my original contention that Marty might have done this. There doesn't need, no digit in this puzzle needs to appear 9 times. We've already seen A has appeared a lot of times already, a lot more than 9, especially once you take that into account. So this could just be the only cell of orange, but if that is true, then we would be in that world. And that might break for 2 by 2 reasons, actually. Oh, it probably does, doesn't it? Yeah, this doesn't work. This doesn't work. I think it's the same point. Oh, I've got another point. Golly gosh, right, okay, here's another point. I was looking at this, I was trying to say, is that definitely purple? And actually I think it is. Because imagine this was green. So we've got a sort of 2 by 2 with the same colours on the perimeter, or on one diagonal. Can you have different colours here and here? No. And that's because all 3 colours have touched the perimeter. And they have in this puzzle. I just don't know how big I's region is going to be. But the point is that green has to get back to this edge. And however it does it, it's going to isolate that purple edge from that purple edge, isn't it? So in fact, yeah, hang on. So in fact, yeah, so there's a general point here, which is that it's impossible for green ever to touch orange. I mean, obviously I've drawn something strange in the grid here where orange is tiny and where it's very difficult. But I mean, in theory, you could have great slugs of orange. Imagine orange did this, then lots of the grid's going to be orange. But if that was the case, it's still impossible. It's impossible for green to touch orange in any way, even diagonally, but certainly orthogonally. Because imagine the two of them did somehow meet up. I mean, if it's an orthogonal meeting like this, how are the pinkles ever touching each other? They clearly can never get through what would effectively be a wall of orange and green. Yeah. However you build this connection, wherever it appeared in the grid, it would become a wall dividing one half of the grid from the other, and that can never ever work because you'll always isolate these cells from one another. But that logic is still the same if we do that. This is impossible because this can't get through that barrier. So what I'm now saying, I'm saying a lot of things. I'm not sure how many of them are really insightful. But I'm saying that nowhere, I'm saying that cell, row 9, column 9 is orange. I'm saying nowhere in the puzzle, however orange, big orange is, nowhere is orange touching green. Anywhere, but at any side or vertex. And I wanted to think about whether the idea, whether this is actually possible. And the reason I was wondering about this, I don't think this is going to work, is it? Because now I've got 7 digits in the puzzle that are purple. And I know that this row can have 1 repeat. And there's no oranges in this row, obviously, because these oranges couldn't connect up. So the only way of filling this row is with a repeated, you could repeat A once. So I would need an A in that domino to avoid a 2 by 2. But then I couldn't have an A in that domino. It would just, there's no A's left. And I've got to have 8 different digits in the row. So this is wrong. This is wrong. So actually I can say that I has to go a bit further. And now, okay, this is beautiful because now that cell's purple. Because by 2 by 2 logic, it can't be orange. And because green is not allowed to touch orange, it must be purple. And again, if I'm now going to claim all of these are purple, I don't think that's going to work either. In that situation, I've got so many possible 2 by 2s, and I can only use 1 green to avoid it. It just doesn't work, does it? It's quite clear. I've got one. I need 3 greens, so I need 3 repeats of the A. Won't work. So I can go a bit further, and I might be able to go further still. I'm certainly going to try. So if we're in this world, now what's this one in this world? Well, no, see, that could be, yeah, I don't think it matters to the question. But maybe it does actually. Because that can be orange or purple. I mean, it can't be green. But I still think it's a problem. Because I can't make both of those purple. So one of those has to either be orange or green. I've got 3 orange digits. I've used one of them here. So I could use one of them there. Actually, maybe it's okay. One orange here. I could use one orange there. So if that was orange, and there was an orange, if that was orange and that was orange, I haven't got a 2 by 2 anymore. Oh, that's distressing. Okay, so I can't. There might be a reason, but I'm not prepared to commit to that. So I think we're here, and that's the limit of my Yin-Yang-Yong thinking. So what have I actually learnt from this madness? I've learnt that I've learnt A and B sum to 10. Well, actually, they're not. Okay. Oh, that's okay. I hadn't thought about this at all. Right, but look now. I've got A and B on a 2-cell whisper, and A and B across an X from one another. So what that means is, I should do that just to make it clear that these two are definitely different digits. So they're different colours as well. So there's a region border definitely there, isn't there? Actually, I should draw these in. That's all I think legitimate stuff. But what I was thinking is, because these have to be 5 apart, and yet they have to add to 10, 4 and 6 won't work. 4 and 6 are not 5 apart. 3 and 7 will not work. They're not 5 apart. They're only 4 apart. So actually, the possible digits now for A and B are 1s, 2s, I don't know how to put this in, 1, 2, 8, 9. That's what A and B are. They're either a 1, 9 pair, or they're a 2, 8 pair. And I'm wondering whether I can use... Yeah, A can't be 1, I don't think. Yeah, A can't be 1, because this thing is saying how many region borders are there in row 8. Now, at some point in this collection of digits, there is a region border, because green is not the same colour as purple. So there could be a green there, but then it'll have to go purple, because green can never touch orange. So there's going to be a region border there. And then there's another region border between purple and orange. So A is not 1. So, oh no, that's lovely actually. It's really clever. It's really clever. A is not 9 either. Because there are only, but how do you divide 9 different cells? There are 8 borders. Ah, that's beautiful. That's really clever. 1, 2, I don't think I need to do any of this yin-yang-yong stuff to realise this. 1, 2, 3, 4, 5, 6, 7, 8. So A can't be 9. So right, this is so clever, Marty. So now I actually know A and B are 2 and 8. I doubt you can put 8 here. If you put 8 there, you've got to have 8 different regions. I mean, I just say, surely that's impossible. And well, actually, you'd have to have 8 different regions here. So what that would imply, I mean, I'm not going to put it in, but you'd have to do 8 black lines. So 8 changes of colour. And then you'd have to have 8 changes of colour there as well, because that one's got a funny thing. But 2 changes of colour. Yeah, so if there were 2 changes of colour, how would that work? That might not be possible actually either. Oh. I'm very unsure about the correct way to think about this, I have to say. If there are only 2 changes of colour, then this row is almost entirely made up, I think, of purple. I think I'm going to get a 2 by 2 in there. I'm not sure. That's my feeling. I've not logically proved that, but that feels to me like what's going to happen. I'm just going to try not to have to think about that, because that feels terrifying. I'm going to just let me think about something else. Is there an easy way of not having to do that logic? I don't see it. I don't see it. All right, so maybe I think I'm going to have to work out whether A can be a 2. And the reason I think that might be a problem is this. If A is 2, that's a region boundary, that's one of the cuts. And therefore the conversion of green to purple is the second cut in this row. Now, the latest that can occur is if I duplicate, because I can only have one duplicate in this row. So I could make that a second A, that would be perfectly fine, but then the whole of the rest of the row is purple. And all of I mean, actually that's immediately impossible. Because I've repeated A, I should have, these are all different. There should be 6 different purple digits in the puzzle, and there aren't. There's a maximum of 5. So yeah, so actually, so it's simpler. I don't have to worry about 2 by 2 logic at all. It's just a count. It's impossible. Because if I then decide to try and make it simpler for myself by saying, okay, well, let's make this not the duplicate, so we say that the cut happens immediately, well, now I've got 7. Well, no, one of these could be a repeat, but only one, which still means I've got 6 different purple digits, and I haven't. That's really clever. I mean, it's difficult, or at least it's difficult for me to just immediately know that 2 is impossible there, but it clearly is. But you have to think it through, and I thought it was going to be to do with 2 by 2s rather than sort of unique digits, but it works. It's in a way it's cleaner, isn't it? That it's got to be. Right, but this is huge. So I now know. Well, this is huge, but also surprising. I now know A is not 2. So A is 8. I think I can just make it 8. B is 2. And we can get rid of all of this and put 2 and 8 in. But I think the real point is going to be this. Well, both of these rows are mad now. Because I've got 8 actual region differences along this row and 8 actual region differences along this row. Well, is that going to finish the puzzle, Sam? Right, purple now has to get out of it. It's been put into a cul-de-sac here, so it's got to get out because I know I've got some purples elsewhere. So this digit, well, this digit we know can't be green because green never touches orange. So this is only able, this must be orange. And this digit can't be purple because there's a region division, and again it can't be green because then green would touch orange, so that's also green. So right, so both of those by that logic are both purple again, because we know we've got to keep remembering, and I keep having to remind myself that green can never touch orange in this puzzle. You see, here it's different, isn't it? There might be a reason why, but I don't think it's necessarily true to say that those two cells can't be green, because they're not touching an orange, so it's not totally illegal. It's not obviously illegal for them to be. So if what about that one? That's touching both colours. So if this was, it can't be orange therefore, and it must be different from green. So that's purple, which means that's purple because that's just the extension of that logic, which means both of these digits are 2 because we only put 2s and 8s into this column. But I know none of these are green, so all of these are purple or orange. Oh wow, it's still not easy, is it? Oh dear. Oh, it's not this Nabna, is it? No, I don't think it is actually. I was just thinking, a Nabna line can't have consecutive digits on it, and I've taken 2 and 8 out, but 2 and 8 in a way are lovely digits to take out. If you imagine the digits 1 to 9 laid out in front of you, if you take 2 and 8 out, 1 and 9 are lovely digits to put on Nabnas, because they can only be consecutive with 1 cell each anyway, and the 2 and the 8 have gone. So this has probably got 1 and 9 on it. And then there's a lot of flexibility about the other 2 digits, because they just have to be 2 non-consecutive digits from the digits 3 through 7. Oh dear, now I really don't know where to look. I think I probably have to... Okay, what about this? Yeah, I can use the arrow to say that can't be green. The only green digit is 8. If I write 8 there, it's wrong because of the blue arrow. There can't be 8 region divisions here. There's only 7 dividers, I think. The only way you can create an 8 on an arrow is to have it in the perimeter of the puzzle. So that is not green for that reason. It's not purple because it's differentiated from purple, so that is orange. Orange can't touch green ever, so that is orange. And now the big game in town is to know what that cell is. Because if that's orange, we can't have a checkerboard, so these would all be orange. And if that's purple, then all of those are purple. Oh no, that would work. I was thinking that just doesn't work, but these are orange, then we can extend orange a couple up there, can't we? That would be totally legitimate. These would be purple. Wow, I don't know. Wow. It's not very easy to do this. It really isn't. It's not that, is it? It's not this X. Like, there's no way. I'm just wondering if that has to be that. These two digits have to be the same. How could that must be true? Even if Marty's done his thing and this is a 5. 5, 5, 5. They're still the same. Yeah, this is really important, actually. That's beautiful. It's beautiful because it's sneaky. Yeah, I think these digits are the same. Let's just experiment with that. Let's say this digit is the digit 7. What am I writing into this? Well, it's an X, so this is a 3. But then what am I writing into this? This has got to be 7. These have to be the same digit. Even if we're in nonsense land, these are all 5s, and these are still the same digit. So this digit, because it's the identical digit to this is orange. And why am I excited about that? Now I've got to get purple out. And that means purple comes into the perimeter here. And I can't introduce any other colour along this stretch. Let's remind ourselves why that's true. Let's make that orange. This orange has to connect to this orange, and however we achieve that, that purple is, we can already see that purple's isolated. It won't work. So all of those are purple, which means, because we've now got 5 purple digits, there are 5 of the digits 1 to 9 are definitely purple, and this column needs to have those 5 digits in it as well. Those are all purple. And now I've got to get this orange out, so that's orange. I've got to get this orange out, so that's orange. Orange can never touch green ever, so both of those are purple. That one I'm not so sure about. I mean, I know it's not. I know it's not purple. Let's just make that clear. Let's make that clear. Make that clear. That clear. That clear. That is definitely orange. Again, if it was green, green and orange would touch at a vertex, and we worked out that didn't work, and we must avoid a 2 by 2. We must avoid a checkerboard here for the same reason, so this has got to be orange. That's got to be purple. It can't be green, or it would be touching orange. This is it's a fantastic puzzle. I'm finding it very hard because I'm not good at this weird rule. But I'm also finding it very interesting, and when I do eventually get to the deductions, they're so clever. You can't deny it. It's just brilliant, isn't it? So these digits here are now G and H, because they must be those digits, but not necessarily in the same order. Now, what do we do next? Well, that's a very good question. And I don't know. I don't know. I know these digits are C, D, E, and F. And these are all non-consecutive digits. And how is that working then? So Yeah. Let's look at this. This is an entropy line. It's the same as this, isn't it? It's not Dutch whisper. It's entropy. Now that means that in every 3-cell stretch along the entropy line, we've got to have one low digit, one medium digit, and one high digit. There's something there. There is something here. So let's just quickly... Yeah, but because what that means is this digit's entropy has to repeat here. Because this digit's entropy, let's say that this was, I don't know, let's say it was a 3. If this is a 3, then in these 2 cells you're going to have a medium and a high digit, but in those 3 cells you haven't had a low digit's entropy, so this has to be a 1, 2 or a 3. So this one's entropy repeats here. Not the digit, the entropy. And then it repeats again there, but this one's entropy, let's use black. That repeats here and here. So these digits, which are they are non-consecutive. So I have a feeling this is absolute genius of Marty, actually. Yeah, it is. It is absolute genius. The point here is that, yeah, this is absolutely ridiculous. It's ridiculous. I think, I might be wrong about this, but I think I don't think any of these digits are from middle entropy. And the way I'm seeing that is weird, but basically we know that this line now, it contains 2 of the same entropy set. So let's say that it contained 2 high digits. 2 from the high entropy, because it's either containing, well, it's containing 2 blues and 2 blacks, so it could well have 2 high entropy digits on it. But those digits have to be non-consecutive, so they couldn't include the 8. So from the 7, 8, 9 set, you couldn't include the 8. I mean, actually, you can't include the 8 because of this, but you couldn't include the 8 as a principle, because once you'd included the 7 and the 9 from that set, 7 or 9 are definitely consecutive with 8, and you break the Nabner rule. But that's going to be the same for all of the sort of 2 mod 3 digits. So you can't have a 2 on that line. You can't, I mean, we could see that as well, but you can't have a 5 on that line. Because if you have 5, you will have 4 or 6, and they will be consecutive with it. So that won't work. Why is my watch buzzing at me? Let me just check. That's nothing important. It's not. It's an O2 bill. Now, but here's the point. Here is the kicker. So now we know that the digits that comprise C, D, E, F are either a 1-3 pair, a 4-6 pair, or a 7-9 pair. That they have to be selected from those 6 digits. What would happen if we took 4 and 6? If we said that this collection of digits had 4 and 6? Which one of the other pairs are we going to put on? Because if you've got 4 and 6, you can't have 1 and 3, because the 3 will be consecutive with the 4. And if you have 4 and 6, you can't have 7 and 9 because the 7 will be consecutive with the 6. That is absolutely ridiculous logic. And that, in that microcosm, we capture, we're able to actually see, and we can just glimpse for a moment inside the head of Marty Sears and know that he sees numbers in a way that it's just transparently beautiful. So Marty is able to somehow see without context, because this is, it's hard for me to see it when being presented with it, with it being there in front of me. I can see it, but to be able to come up with that in a vacuum is just that a Nabna line with 4 digits on it, and then you'd put the entropy line up there where it has this, it forces the middle digits off this, is just, it's breathtaking. Yeah, it's breathtaking, and it's massive for the puzzle, actually, because now we know that C, D, E and F have to be, they can't include the middle entropy digits at all. So they are the digits 1, 3, 7, 9. Oh, didn't mean to do that. I wanted to get rid of the... They are the digits 1, 3, 7 and 9. And if this was a 1, that will be a 3. And if this is a 7, that will be a 9. These are from the same entropy set, and these have that quality as well. And now, G, H and I, actually we may as well abandon them, they are the middle entropy digits. So all of these digits are 4, 5 and 6. And now, yeah, we've got to be very careful with this, because this looks like it's a blue entropy digit, which looks like it's sort of copying the entropy of this. But that one, imagine that was a 1. That could be a 2. Yeah, I'm going to get rid of those 2 colours. I think it's dangerous. I might leave these in because I'll understand those, but I'm not going to label those 2 because I think I'll automatically default to thinking they're necessarily these digits, which I don't think is true. Right. So is it this line now? That's got to have an orange on it. Because this is an entropy line. It's got to have a 4, 5 or 6 on it. I mean, obviously that's not here. Oh, yeah, I do sort of see this. Yeah, look at this line. Now this line has got on it, it's this is column 3. So there are 3 different digits that appear in this column. Now, I can see one of those digits is the digit 8, which is a green digit. I can see one of those digits is the digit that, whatever that is. And I know there's 1 orange digit on it because I must put a 4, 5 or a 6 in this sequence. But so now, could this digit ever be the 8? No, because if it's a green 8, it's going to touch the orange, which we know is illegal. By a similar token, could this digit ever be orange? No, because it will touch an 8 on one side of it, and that's illegal. So I think you have to put the orange here, because this can't be orange. It would, well, for many reasons, but amongst them it would touch green. So I think that's orange. And then we know this one can't be the green one. So that's got to be the purple one, which is the same as this one. So this is 1, 3, 7 or 9. And these are the same. I'm going to give those a letter, I think, to try and remember that. And then this one must be 8, because I must have. Oh, hang on. This is okay. So this is doing even more magic, isn't it? I'm not sure how far the magic's going, but this being 8 means this can't be 7 or 9, because 8 and 7 and 9 are in the same entropy set. So this digit is now 1 or 3. Now, does that transplant up there? Yes, it does, but not through this cell, but through this cell. Because in this row now, I need 3 different digits. I've got 2, 8, and the digit A, which is 1 or 3. So this can't be 7 or 9, or there would be 4 distinct digits in this row. So this is 1 or 3. So this is 1 or 3. So these are 7. These are a 7-9 pair now. They're different, remember. But now the entropy of this, is 1, 2, or 3. It's low. The entropy of this is high, which is 7, 8, 9. The entropy of this is middly, which is 4, 5, 6. And that one is definitely orange. Oh, Marty, it's absolute genius, this puzzle. And that now can't be 8, because that would make orange touch green. So that's 7 or 9 and is pinkle again. Now we can't have a checkerboard, so that's pinkle. And we can do that. And that is legitimate. And right, and 1, 2, and 3 are always in this puzzle pinkle. So that's pinkle. We just don't know whether it's 1. It could be A, or it could be 2. We don't know. But this one, bobbins. Well, no, not bobbins. Good. What's this digit? I was going to say, well, it's not purple or pink. It's definitely something else. So it's orange or it's green. But actually, if it was orange, it can't be orange, because one of these is a green 8. And it doesn't matter which one it is, it will touch this at least at a vertex. So this is not orange. This is actually green and is an 8. I so want to now make this a 2 by mistake, but that's just not how the puzzle works. So, okay. Okay, I don't know what this means yet, but that's all jolly exciting. This digit is a 2 or an 8, and it can't be an 8, or it would touch orange. So that's a 2, and the same logic's there. Again, we can never make green and orange touch, even at a diagonal. So given we only have the option of 2 or 8, that is also 2. Now I don't know what to do. I mean, it would be if all of those, if that's 8, all of these are 8. And I have a strong suspicion that would have to be 8 as well. Can we see an issue with that? Is that possible? Oh, well, I was going to say no, that doesn't work, but that's not true. Is it that green line? I don't think it is. I think you can absolutely have. I was wondering if both of the... Well, no, I mean, actually, no. Okay. I was wondering whether you couldn't put an orange on the green line, because orange obviously includes some of the most difficult digits to place on a green line. Orange includes the digit 5, where you can't put 5 on a green line full stop. It also includes the digits 4 and 6. Now, if you do put 4 and 6 on a green line, they only have one partner. A 4 can only partner with a 9 because it's the only digit in Sudoku or Sumdoku that is 5 different from the digit 4. 6 can only partner with 1 for the same reason. Now, that does mean that this could be an orange-pinkle pair. Okay, so I can't do that, I don't think. Row 3 has no orange in it. It's got a 1 or a 3, a 2 and an 8, and that's all the digits it's allowed. So this does not extend any further. So that's capped out, and we know, and therefore I know the colour of this one, which can't be green. So that is right. So that's pink or purple. So this is now green to avoid a 2 by 2, which is the digit 8. This is now 2 to avoid a 2 by 2 there. Now, what's this? Surely I know. If that's 8, that looks okay. This would be 2. All right, let's try it the other way. If that's 2, the 8 would be trapped. So the 8 would come here. This would be 8. Oh, bother. I don't know then. I'm not sure I do know. Okay, that digit is 1, 2, or 3 because we know its flavour in the row. Oh, right. Row 4. What are we allowed to put in row 4? I've got 8 and 2, so that's 2 digits. I've got a 4, 5, or a 6, or possibly more than 1, but that's a 3rd digit. And I've got a 7 and a 9. That's a 4th digit. So actually, I'm now learning that those 2 digits are the same digit. They can't be different. And this digit is the same as that digit. Right, so what I'm going to do is I'm going to change my shading. I'm going to make that. These are actually the same. This is different to this because it's in column 9. So these are definitely the same. Now this is therefore 2, 7, or 9. So we might have to think, oh no, it's a Nabna. Okay, that's not probably that helpful. Now, we have got another arrow in this one, which I've never looked at. 1, 2. So far this could be a 2. If it's not 2, it has to be 4 actually. That is 2 or 4, because that's just how many barriers we can create. How many black lines can I put vertically between this cell and the edge of the grid? 1, 2, 3, 4. So it's 2 or 4, but 4 is possible. 4 would make it orange. 2 would make it pinkle. It would make that pinkle. It's probably harder for it to be. Ah, that's done it. Beautiful. It's very simple. Again, it's a lovely selection of a clue. If it's a 4, what colour is it? Well, it's orange. But what we would then be doing is this. And what on earth colour do we make that? It can't be orange and it can't be pinkle. So it's green, and green touches orange. That's simple. That doesn't work. So this is not orange. It is 2 actually. It's definitely 2, which is definitely pinkle, which means that's pinkle by checkerboarding. This is orange to get out. That, oh, has this been available for ages? Sorry. Look, that's got to be purple to avoid a 2 by 2. So if that's purple, oh, all 3 of those are green. And if that's green, these, hang on, if that's So is this always green? If it's not green, it's purple. And we get a checkerboard. Yeah, you can't, because this can't be orange because it would be connected to green. If we make that purple, this would be green to avoid a 2 by 2, and that would be purple, and that's 2 by 2 is a checkerboard, which cannot exist in the puzzle. So this digit is a green 8, and that gives us some more boundaries. Let's draw those in, draw these in, draw this in, draw this in, draw this in. It's definitely progress when we do this. We can do this, 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 this. I've just got this. Oh, I think we're getting there. It's not been a quick process, but we're getting there. Right, this is 1, 2, or 3 in the row. That's on a Nabner again. Of course it is. Wow. Okay, and there are only... Okay, I see. There are now 2 boundaries in this row. So, and we've got them. So this digit has to remain purple. So that's another boundary here. And the options for purple into this cell, well, this can't be a 2 because it will be consecutive with this, or it'll be the same as it. So this one is 7 or 9, and it is the black digit. So that one is the black digit. And that can never be consecutive with this, so that's really not going to tell us a great deal more about the world, I don't think. Right. Now I don't know what to do. Right. You can't... It must be this, I think. I don't think both of those can be purple now, because that's going to fence off this orange. This orange can never connect to its friends if both of these are purple. And definitely neither of these is 8, because 8 is green, and the green will touch an orange in either position. So this is one pink and 1 orange. Now the orange is going to be a 4 or a 6 then. So these digits are 4, 6, 1, 9. And presumably, because if it's a 4 from orange, that has to go with the 9. So, what does that mean? Have we got the count then on this column? We probably have, haven't we? Hang on, I've made that purple is the digit 2. It's definitely not the digit 8. Right, let's count column 4. I've got 1, 2, and these 2 are different and are not 8 or 2. So these are the other 2 digits. So this, oh no, that could still be a 1. It can't be a 3. Definitely can't be a 3. But if this was 6, 1, it could be a 1. Oh, you've got to be so careful with this. This digit can't be 3 or 7. These digits then are either 1, 9 or 2. I'm sorry, I thought that was going to do something, but I don't now think it does at all. In this column, this is a 4, 5, 6, obviously, because it's orange, but it's also exactly equal to this. These are the same. And that's because this is column 3. And these are the only 3 digits that appear in this column. 8, a 1 or a 3 pinkle, and a 4, 5 or 6. Now, I don't quite know what that means yet. So, yeah, I do. Well, how could this be green now? If this is green, green has to get out, and to get out it would go straight up and touch orange. So this is orange. So orange has to get out. So this is all orange, and all these digits are the same. They're all 4, 5, 6, and they're all B, whatever B is. So those are all the same digit. Now this digit now can't be 8 because it will be touching orange. Oh, this puzzle is fantastic. It's difficult for me, but it's fantastic. Right. So now it's going to be these funny difference lines that somehow differentiate the digits, isn't it? But we're doing okay on the Yin-Yang-Yong shading without having to resort to them. Okay. Right, what do we do next then? I know that's the digit A. That's the digit A. So is blue... Oh, see, I've got the... Okay, so I'm going to change that one. These are different. Whereas that is the same as that, I think. And the same as this. Does that help me? I'm not sure. We've somehow got to... We're still definitely not done yet, are we? No, what I was about to say is not true, so I should refrain from saying it. That has the possibility of being a 2 by 2 if that's pink. So that's got to be orange. So that gives us a little bit more of the shape. Oh, this is evil. So this is ambiguous. We don't know. This is going to come down to a count in this row, isn't it? Or this row, as to what extra digits you can possibly have. And that is totally and utterly frightening. That's very, very... Well, maybe we can do it straight away. What's this digit? That's a pinkle digit, which is 1, 2, 1, 3, 7 or 9 on a funny line. Oh dear. These digits. Oh, what's this? I must be able to do this. What's that digit? That's on a funny arrow thing. And I haven't got many regions. 1, 2. But it can't. Yeah, this is important. So if this was green, then there's only 2 regions. This should be a 2. So that's definitely not green. That's 2. That's 8. We can do the color. Oh, whoopsie. We can do the colors up here. So 2 is pinkle. That is how this top bit unwinds. And I think this has to be a 4 then. 1, 2, 1, 2, 3, 4. That is a 4. I don't know what that means for those. This is column 5. So we've got an 8 and a 2, a 7 or a 9. That's 3 different digits. We've got this digit, which is a 4th different digit. So either we just don't know, do we? I mean, it depends what this is. If that digit is a black digit, if it's that digit, 1, 2, 3, 4, I'd need a 5th different digit, so I'd have to have a 5 or a 6 in one of those. But if that digit is not this digit, then all of those digits would be a 4. I don't know. Okay. So actually we've really nearly done the shading then. Let me just think about it. I have really nearly done it. Is this the only ambiguity? So it's got, right, so it's the other weirdo lines are going to have to figure this out. That's what we're going to have to do. And actually, that's really weird that this all gets figured out by that, isn't it? It's weird to me, at least. Possibly with a healthy dose of, oh, we need different digits all over the place. I suppose I know those digits are different because they're in row 9, so those are not the same digit. So that could be, if that's a difference of 1, it's either a difference of 1 or a difference of 2, isn't it? That's what's going on this line. So whatever... Yeah, so whatever... So these two have the same parity. That must be true. That this is right. That might prove this is a 5 actually. Yeah, look at this row. And I'm noticing in this row I have 4 orange digits. Therefore, there are only 3 different orange digits, 4, 5 and 6. So there must be a repeat within the orange digits there. Now, but this is row 8. So there's only 1 repeat in this row. So one of these orange digits repeats, and the others have to be different. So there's a 4, 5, 6 set within those orange digits with 1 repeat. But that means that all of the purple digits in this row have to be non-repeating, because otherwise we'd have a second repeat in row 8 and we wouldn't have 8 unique digits. So this is not a 2. These 3 digits are from 1, 3, 7 and 9, which are my other pink digits. And that digit is odd. And I think it's got the same parity as this. Because whatever the difference is on this line, you're either, the difference between these is x and the difference between these is x. So it's you're either going up by 2x or you're staying the same. So the parity should be the same. And that's odd. So that's 5. And therefore these are not 5 because that's row 9. Now we can't say the same thing in the column. Bizarre. Oh, no, we can. We can say this is not 5 because the difference is now 1 on the line. So this is now 3 or 7. Yes, okay, so whatever it is, these 2 digits are now the same. And this is very hard to keep track of. Because if this is 5 and this is 4 and this is 6, this digit would have to be a 5 to be consecutive with both of them, and it wouldn't be. So these are the same. So it's either going to be 5, 4, 4, 3 or 5, 6, 6, 7 is how it's going to work. Oh, goodness knows what that means for this column though. So I do need lots of different digits in this column. I've got 1, 2, definitely different. 3, 4, definitely different. 5, definitely different. And then who knows what after that. This is okay. It's still definitely not easy. Wow. Okay. I'm sorry if you can all see what I'm meant to be spotting here. I am not spotting it. That's very, very clear to me. I think I'm going to end up with a very heavily pencil marked grid again. Or is it going to be... Okay, so let's think about this. I've got 5 different pinkle digits, 3 different orange digits, 1 different green digit. I don't think this matters, does it? Oh no, it's going to be this column. This column I've had a repeat in. Yeah, so it's going to, I think it's going to become a colouring exercise then, actually. These pinkle digits are all different from each other, including that one. So 1, 2, 3, 7, 9 are the options. Wow, I don't know. I mean, if this was a 1, they could both be 4. 4, 1, 4. Or 5, 1, 5. 6, 1, 6. That would totally work, wouldn't it? I mean, yeah, I don't... Is the idea to say these 2 digits are the same? Perhaps that's the point. Maybe that's the point. How would these be different? If they were 4 and 6, yeah, that doesn't work. So these 2 digits are the same. Yeah, I probably am going to have to colour everything, aren't I? I think that's probably what's being required of me. But I've got occasional digits which are B. So okay, let's try and colour within orange. I'll try and do that. So within orange, what colour should I use? Yellow? It's difficult for me to see that. Although I'm running out of good colours, I'll have to use. I'll use red. I'd really like to use green, but okay. Let's use red now. Or maybe what I'm meant to do is to, because I know these are different. Oh, I don't know. I'm not sure. I'm not sure what the way to do this is. Or maybe this line will be easier to figure out. Maybe that's the place I've got to look. In this column, what have we got going on? It's column 6, so there need to be 6 unique digits, but we've already had 2 repeats. So we could have 1 more repeat. Or to put it a different way, we must have 1 more repeat. 1, 2. And then of these 5 digits, 1 is repeating. But that might... Okay, we might be able to deduce what's going on this same difference line then. So let's just fill this in. 1, 2, 3, 7, 9. 1, 2, 3, 7, 9. Now... Well, the difference is clearly not 0 between these 2, is it? And if the 2 is involved, how can that work with this digit? I just don't think it can. Doesn't that have to be a bit like a thermo? Like I could see 1, 3, 5, for example. That worked. 9, 7, 5. If we use an even digit here, there's no way. What's the difference down to this? If we use the 2, the difference is even and this is unfillable. If we use the odd digit, the difference is odd and this cell's unfillable. So this is never... Yeah, this is never a 2. So the difference isn't, the difference is even. So this needs to be an odd number. Okay, so that's 5. And then this is obviously odd as well. But you could go 1, 3, 5, 7, couldn't you? And all 4 of those could be different. Or you could go 1, 3, 5, 3, and then they wouldn't be different. Oh dear. But it does operate a bit like a thermo, I think. So I don't think this can be a 1 or a 9. Because I think this, on that analysis, if this is 1 or 9, the difference is 4 on the line, and this should be a 5, which it isn't. So so this cell is 3 or 7. And the difference is 2. So this cell is also 3 or 7, and this cell is now definitely 1 or 9. Now, do those have to be different? Oh, maybe they have to be different. Yeah, that's true in this row, isn't it? Because in this row, we've definitely got a repeat within orange, so those are definitely different. But I don't know if these have to. These probably don't have to be different. In fact, maybe they're the same. Because we've got an 8 and a 2. And then either 4, 9 or 1, 6. So these are the same digit. So those are the same. I'll just label that with a letter. These are the same. And this is the digit E. That's different. And now I've got letters and colours going on. Oh no. Oh no. And I still don't know whether these are different or not. Okay. Goodness knows what to do now. I don't have a clue. Sorry if this is easy for everybody. I am fully cognizant of the fact that I am not finding it easy. Is it the same thing there? Do I know those are the same digit? I feel like I do. Because whatever this is, we're either going down by x or up by x to it. And then we're going to have to go, that can't be an ascending, it can't be a thermo sequence, can it? Because this can't be a middly digit between these two digits. So these are the same digit. So maybe, so these are the same digit. Oh, hang on, that's a 5. That's on my series of x's. Oh, hang on, these are 5s. Ah, this is it. Right. I mean, look what Marty's done there. It's classic Marty. Just completely bowling over your expectations. Now, hang on. So that's a 5, so I think that's a 5 as well. So this isn't a 5 because that's in row 9. So these two digits are the same. So these two digits are the same. And they've got to therefore be 6. I mean, that's sick. That's a 6 series of deduction. I think that's right. Let me try and do that again. I worked out earlier that those are the same. I've just worked out, well, whatever this is, because it's in column 9 and row 9, that digit is different from these two. So these two are now the same. But I just said that was the same as that. So in this row, these two digits are the same. If they were 4, I've got too many repeats in this row. So they have to be 6. That has to be 6. That has to be a 4 in the corner. This has to be 7 by that logic in order for this to form the same difference sequence. We can't do Sudoku. Just forget Sudoku. You can't do it. You're not allowed. Now, but in this row, we've now had our repeat. We are only allowed one repeat, so that digit is a 5, and that is the digit B. So all of those are 5, and that is 5. And I've got an absolute plethora of 5s that have just emerged from nowhere in this grid. Now, I've now had 2 repeats in this row, so I'm not allowed any more repeats. So this is definitely not a 5. And I'm not allowed to repeat a 2. Right, this digit is D, isn't it now? I think. Because whatever digit, the only Pinkel digits I have in this column are 2 and this digit. Because I have 8 and an orange digit as well. And I can't have more than 4 in column 4. So these are all the same. That might be important at some stage. These are different. So that's not a 2. That's got to be a truth. I don't think it matters what it is. Oh, maybe it matters for this column. Yeah, I've had a repeat in this column, so it's not 7. So this isn't 7. I can't have another repeat, so that's got to be 4. And that's on this funny line here. But this row needs a lot of repeats and a lot of the same. So the middle rows are just horrific. Oh dear. Okay. I promise you, I'm trying to figure this out. It might not look like it, but I am trying. What about this row then now? That's row 5. 1, 2, 3, 4, and this digit seems to be a 1 or a 3, which I haven't said. So those are the digits that I'm allowed to put into this row. So doesn't that mean... Well, oh no, that could be a 1. Okay, but this digit is 1 or 4 now. There are no 6s and no 9s in this row. So this is 1 or 4, and this is 6 or 9. And there's no 6s in the row, so that's a 4 or a 5. There's no 6s in the row, so that's a 4 or a 5. And this, oh, hang on, you can't put 7 in this row. You just can't do it. So this is, yeah, these two digits are the same, is one way of putting it. So they are both 3. So we can give that one an indigo flash. So the difference on this line is 2. How is that possible that that doesn't resolve that? And yet I don't think it does. Incredible. It's incredible. But if that's 3, that's got to be different from my blue. So that's 1. So that's 1. Now this can't. Now that's 9. So all 3 of these are 9s. Now in this column, I have to put 9 on here, don't I? If I put 6, 1, I've got too many digits. So this is 9, and this is 4. And now I can do the colouring. So this becomes orange. That's 9 is the purple. So that is the final piece of the shading done. In row 3, the digits we use are 1, 2, and 8. So we don't use 3s. And somehow or other, this has all got to be figured out from here. It still seems incredibly unlikely that this is going to be uniquely solvable, but I'm sure it is. Okay, these are now 3 and 7. which is fine, I think. In this column, this is column 5, we've got 8 and 2 for 2 digits, the 7 or a 9 for a third, some congregation of oranges, that's 5, that's 1, 2, 3, that's 4. I need one more. So it depends whether this is different. There's probably a way I'm meant to know that. Yeah, I wish I knew. Ah, here's something. This column is really... Oh, this is good. This is good. Look at column 7. I've had my 2 repeats. I've got 3 5s. I can't have any more 5s. So that's got to be 4. Everything else has got to be different. So that's got to be 1. Oh, bobbins, and that can be either. But that gave me another digit here. That's the... Gosh, this is taking me so long. I'm going to get to 2 hours at least, aren't I? But I might be able to do it. That's the main thing. Can I do it? Right. In this row, we've had a repeated 6, so I can't repeat the 9. So that's a 1. I had labelled that as E, but now this has got to be 3. So that's lovely. We get a little bit of a bonus here. Now, can that be 7, I wonder? This might be important. I've had... It's column 6, so I've had 1, 2, 3, 4 digits. I need 2 more different digits. So I can't use 3 again. That's got to be 7. That's got to be 3. And now this is different from that. 1, 2, 3, 4, 5. And this is column 5. So all of these are 4s now. So that doesn't break the world. Now what about this row? I've had my repeats. They're 5s. So I can't... So this is different. So that's a 1. And the difference on this line is 4, which is ludicrous. Now this is not a 1 anymore. And this is not a 1 anymore because we've had our repeats here. So this is 2. How does that ever get resolved? Have I broken this somehow? Ah, no, it's going to be this column. 9, 4, 2, 8. So I'm not allowed a 1. That's got to be a 2. Right, that's great. Okay, so in this column, I've got 1, 2, 3, 4, 5. I need a 6th different digit, so that is not a 7. But it could be a 2, apparently. Ah, but if I worked out those were 7s, that would affect this. So that's probably what we have to do. Is it going to be this row? This is row 6. Okay, why is my phone buzzing at me? Now row 6, I've had 3 5s. So 1, 2, 3, 4, 5. I've had 5 different digits. I'm allowed 1 more different digit. But I don't know what this is. Or is it something to do with... Ah, hang on, I've had a 2, so I can't have a 2 there, because I'd have a 2nd repeat in this. So this is 3 or 9. So one of these is a 9, because this can't be a 2-3 pair. That would break everything on the Nabna. Oh, and you can't put 3 on it at all. Oh, that's it. Sorry, I didn't spot this, but I've got 4 on the Nabna at some point. So now this can't be 3. So this has to be 9, and now that can't be 9 because it would repeat. And if that's... I don't know what this means yet, but I'm hoping this figures it out. I've done lots of it now. It's so embarrassing. Right, let's look at row 6. I've got 1, 2, 3, 4, 5 different digits. I need a 6th different digit, I think. I think that's going to have to be 7. 1, 2, 3, 4, 5. I think I need a 7. So that's 7, and that's 9, and that's 9, and that's 9, and there you go. That is a brilliant puzzle, if that's right. Okay, it's 2 years old. Wow. Oh my goodness, that's brilliant, isn't it? What a contrast to yesterday. That's like Marty Sears is sort of, he's been Taravangian on a bad day. Very, very clever, but just hasn't really opened up his mind. Then all of a sudden he lets you have it. There you go. That's what you can do if I just turn it up to 11. Brilliant. It's a brilliant puzzle, completely mad, and I loved it. Yin-Yang-Yong. Let me know in the comments how you got on with it. I enjoy the comments, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.